Hi guys, hope you all preparing well with our course content. So here in this video we are going to analyze today's chemmasters challenging MCQs on advanced organic chemistry. I hope all of you tried each and every question in this series, and here you are going to get the detailed conceptual solutions, and please try to rectify your conceptual errors and where you have done mistakes while solving these questions. Okay, right. Now look at the given question here. And before that, I always suggest our chemistry that if you practice these kind of questions, I guarantee your success in any level of examinations on chemistry in India. Okay, right. So please keep an eye and practice the questions which you come across through chemmasters courses. Okay, right. Now, what is this structure? Can you say the name of it? So that is a signon. Okay, we know that signones are very important aromatic compounds. Signones exhibit aromatic nature. Okay, right. And what is a unique feature of signone? Can you say? Here, signones are always in ionic forms. That means signones never be drawn in neutral forms. Okay, so signones can only exist in ionic form, and they are not going to exist in neutral structures or neutral forms. That is a unique feature of signone. Okay, now here I'm going to draw the possible resonance structures of the given signone. Okay, so here this is the structure we have given as a reactant, so which can be drawn in the perfect ionic nature or ionic structure of the given signone, where one of the nitrogen must be positive because one of the nitrogen can have valency 4. Okay, and here is the one resonance structure of it. And in the next case, so the negative charge on oxygen moves here, then this bond just moves here. Okay, and this double bond moves onto nitrogen, and here we are going to produce another possible resonance structure of the given signone. So here C double bond O, and here is the negative charge, and here the nitrogen again with the positive charge because of it is having valency 4. Okay, right. In the next step, we know that nitrogen is more electronegative than carbon. That's why the pi electrons easily dragged onto this nitrogen to compensate the positive charge on it. Okay, right. So in this case, we can draw another ionic form of the given signone, where this nitrogen is with negative charge, and here you can see this carbon is with positive charge. Okay, so this is the structure. Here, this is 1,3 dipolar ionic form, or what we can say 1,3 dipolar structure. So this 1,3 dipolar structure is going to react with acetylene. So we have taken acetylene in the reaction. Now the negative charge on nitrogen is going to attack on this carbon of acetylene, and then the pi electrons of acetylene is going to attack on the carbocation of the 1,3 dipolar structure. Simply, the reaction is taking place through the concerted mechanism, and we can say 1,3 dipolar addition, which is very important concept nowadays. Okay, because the reactions are taking place through the concerted mechanisms. We know that the reactions which are possible through the concerted mechanisms like photochemical reactions or pericyclic reactions, they are very important and useful for modern organic synthesis in green way. That's why it is very important to focus on these kind of concepts. Okay, right. Now, so after 1,3 dipolar addition, so I'm going to draw the structure here. Okay, so this is the product which is formed on 1,3 dipolar addition. In the next step, we have taken heat. So if you look at the reaction, we have heat. So here in a first step, the breakage of bond between nitrogen and oxygen, the two heteroatoms takes place. And in the next step, the bond breaks here and moves here, and the pi electron atoms moves here. So simply the elimination of carbon dioxide takes place. Okay. And this is the final product we can observe. So what is the option here? You can see fourth option is the correct answer. Okay, right. Simply, so the question is designed by just taking the concept of 1,3 dipolar addition. Okay, right. The next question. Here we have taken naphthalene as reactant, but given with the different reactions and reaction conditions. So what you are observing and what is the difference you are observing between X and Y here? Here the reagents are same, and the what we say the proton source or the solvent is also same. Then what is the difference you observe here? Simply the temperature. Here we have minus 33 degrees centigrade, here minus 78 degrees centigrade. That means the temperature difference may lead to the difference in the formation of the products. Okay, right. So at minus 78 degrees centigrade means very low temperature. At very low temperature, the metal reducing agent reactivity decreases. Okay, so the reactivity of the metal here the reduction takes place through the single electron transfer. Okay, right. So the reactivity of the reducing agent decreases at very low temperatures. That's why only one double bond of one of the ring gets the reduction. That is simply partial reduction takes place. Okay, so due to that partial reduction, the two possible products may be observed. So this is the one, and the second one is this one. Okay, so these two are only partial reduction takes place at very low temperatures. Now, in this case, the option X may be in all of these. So all of these are possible. Now, what is Z? So here the temperature increased slightly. So till to minus 33 degrees centigrade. So by just increasing the temperature, the reactivity of this metal reducing agent increases. And in that case, the two of the double bonds of one ring gets the reduction. And in this case, so one of the ring completely reduced. That means two double bonds are reduced. Okay, so option may be in between 3 and 4. Now what is Y? So here the metal is different. Here we have taken lithium, here is sodium. So the reactivity of sodium is more when we compare with the lithium, and it is the selectivity is increases, and the reaction is taking place in aqueous solution, and in that case both the rings of the naphthalene gets affected. That means gets the reduction and produces the final product like this. Okay, so option these two are same. That's why a student can choose option 3 or 4. Both are the correct options for the given reaction. Okay, right. The next question. So here we have taken tertiary butyl lithium and butyl lithium. What is the function of tertiary butyl lithium here? Simply the bulk tertiary butyl lithium is a bulk base and which can abstract acidic protons from the reactant. Now we can say these are the acidic protons. Why? Because they are adjacent to the more electronegative oxygen. That's why they are more acidic in nature. So the base can abstract one of the proton from here. So here is a formation of carbon ion, right? In the next step, this carbon ion just moves here. Then the pi electrons of alkyne attack proton which comes from the reaction medium. Okay, now in the next step, here we can draw the next step, and in which alkyl and the methyl group are opposite to each other. Okay, right. Now in the next step, here it is very important. We have taken butyl lithium. Now butyl lithium is also a base and which can abstract acidic proton, right? Here so many students get the confusion that which hydrogen is more acidic and which can be picked up by this butyl lithium, because if you see if the butyl lithium abstract acidic proton from here, you can get one kind of product, and if it is going to abstract this hydrogen and it is going to produce another product, all of them are given in the options, then which one is the more acidic? So simply we need to apply our basics, that so the proton which is adjacent to more electronegative oxygen is more acidic in nature. That's why butyl lithium abstract this proton only. Okay, now here is the negative charge and then here is the methyl group. Okay, so here the lithium will be absorbed. Okay, the lithium metal will be there. Now it is going to attack on the heterocyclic ring. So this carbon ion is going to attack on heterocyclic ring, and this negative charge on oxygen abstract proton from the reaction medium and it forms a hydroxy functional group. So here I am going to draw the next structure. So here is the OMe. So here is the CH3 and here is the hydrogen. Now in the next step the cleavage takes place here, and then this double bond moves here, and here is a formation of negative charge, and this negative charge is going to abstract proton which comes from that H2SO4. So this negative charge is going to attack on H plus. Now here it is going to produce cis alkene product. Okay, so here C double bond O, here is the OH, and here is the oxygen. So this is the final product. Here the cis alkene substituent is the major product, and so many aspirants gets the confusion again here, why it is going to produce cis and why not trans. So that is the question, and here you are going to get the justification for that. So after formation of negative charge here, you can see the hydrogen is small when we compare with methyl group. So methyl is medium sized group. So this carbon ion abstract this proton from the H2SO4 from the less steric end, that is from the side of small hydrogen. So that's why the two hydrogens are same side. So whenever these two hydrogens are same side, you can get cis alkene substituent as the major product. That's why option 3 is the correct answer. Okay, right. The next question. So here it is fluorine and it is iodine. So please draw them. Now butyl lithium. What happens? Simply whenever we take butyl lithium, here two halogens are there. One is fluorine and one is iodine. So when we compare ortho directing power, okay, ortho directing power of the halogens, fluorine is having highest or strongest ortho directing capacity when we compared with iodine and bromine. Okay, so here in a first step the butyl lithium, the base which abstract proton, okay, and it forms this. So here is the fluorine, here is the iodine, and here is the lithium. Okay, now but as I said, iodine is weak ortho-directing group when we compared with fluorine. That's why iodine lithium exchange takes place. So we call this as halogen dance. Very, very important. Okay, we may get the questions on halogen dance or what we say, a halogen exchange. Okay, so after exchanging lithium and iodine, so here is the fluorine, here is the iodine, and here is the lithium. Okay, so lithium always with the partial positive charge, and here is the partial negative charge. Now this is going to attack on methyl iodide. So this carbon ion going to attack on methyl iodide. Now it is going to produce the next structure where fluorine is there and methyl group, and here is the iodine. Now in the next step, again butyl lithium, the exchange of lithium iodine takes place. Just remember that lithium iodine and lithium bromine exchanges are very common in on aromatic rings. Okay, right. So here, after exchanging, here is the new structure can be seen. So fluorine, methyl group, and here is the what we say lithium. Okay, so negative charge and here on positive charge. Now it is going to attack the next reactant, that is C double bond OH, and here is the methoxy group. So which is going to attack here. Okay, now it is going to give the next step fluorine, methyl, and COH, and here is the just draw the remaining residue OMe. Okay, right. So in the next step, we have taken PCC, that is the pyridinium chlorochromate, which is an well-known oxidizing agent and which oxidizes the secondary alcohol functional group into keto functional group. So here is the fluorine. Now here is the methyl group and here is the keto functional group. Okay, right. In the next step, we have taken HCl. So the lone pair of electrons on ring nitrogen attack on proton of HCl. Okay, so here it is going to produce the next step. So nitrogen with positive charge. Okay, and here is the methyl group and here is the fluorine, and here the remaining residue just draw it. Okay, in the next step we have taken water molecule. So water can act as nucleophile here and it is going to attack here, and then the pi electrons moves on to nitrogen. Okay, and here is a formation of a new structure where here is a fluorine and here is the hydroxy group and here is the hydrogen. Okay, and here is the remaining ring residue. Now in the next step, the elimination of the HF takes place. Okay, elimination of HF takes place and produces the final structure. So here is the methyl group and here C double bond O. So the just write down the complete structure of it. So this is the final one. So the question is designed by just so to check the concept on halogen tanks, which is very important for completing purpose. Okay, so right now next question. So here we have taken another heterocyclic ring and which is going to attack on the electrophile NO2 plus. So just remember that the reaction going to produce the major product whenever the transition state takes place through the more possible resonances. Okay, so that's why the ring oxygen, the lone pair of electrons ring oxygen just moves like this, and now this is going to attack on electrophile. Okay, so here oxygen with the positive charge, new double bond here, new double bond here, O and NO2 plus. Okay, in the next step what happens? Simply once again it just moves here. This is the exceptional that means electrophilic attack on this given heterocyclic ring. So here is the negative charge. Okay, so again here is a negative charge and which is going to attack on the electrophile which is cleaved here. Okay, so from that you can draw. So here is NO2 hydrogen. In the next step, the formation of the reactant again. So simply the final product is the second one. So this carbon is the more resonance, resonance stabilized structure. That's why the nitration especially takes place on this carbon of the given reactant, and which is very important. So just take it. Okay, right. The next question. Here we have taken a pericyclic reaction. That is the question on sigmatropic rearrangements, which is very, very important in competitive purpose. Okay, right. Now, so I'm going to draw the structure in a suitable form for my convenience. So here NO2. Okay, and so just try to check the conceptual lectures in pericyclic reactions in organic section, especially the sigmatropic rearrangements. And here 1, 3, 1, 5 and 1, 7 shifts we can observe. So what are they and how can you say it is 1, 3, 1, 5, 1, 7? So simply just remember that, for example, if we take a 5-membered ring and if the shift of the group or atom, just say X. So if the shifting of this atom or group taking place through the concerted mechanism, through the delocalization of electrons from all of these atoms onto this. Okay, if X is shifted onto this, how many atoms it is exchanged through the delocalization of electrons or bonds? Simply 1, 2, 3, 4, 5. That's why we can say it as 1, 5 shift of X. Okay, so like that. For example, in the same 5-membered ring, if X is shifted from this atom to this only without exchanging through this, then we can say 1, 2 X shift. So just remember that, right? Now I'm going to label the atoms for convenience. 1, 2, 3, 4, 5. Now, so here we need to expand this NO2 functional group. Now, whenever it moves here, then the shifting of double bond takes place, and then the so electron density moves onto the nitrogen, and which is going to attack again on this NO2. So here in the next step, you can see the exchange of NO2 takes place. So not this. So we need to draw the new double bonds here, N, and here is a nitrogen. So which is having NO2. Okay, so you can see the shifting takes place from atom 1 to 5. That's why we can say 1, 5 NO2 shift. Okay, right. Now in the next step, so the same structure I'm going to draw here for the convenience. So here nitrogen NO minus. So in the next step, I'm going to label atoms 1, 2, 3, 4 and 5. So simply whenever the bond comes here, so this double bond moves here and the electrons moves here and these electrons moves onto this, and this electron density is going to attack on NO2. Here you can see the electron density is transferred from this nitrogen 1, 2, 3, 4 and 5. So through the 5 atoms, that's why here, now just draw the next step. Here double bond and the nitrogen here is a new double bond. Okay, and here is the nitrogen and here NO2. Here you can see that here 1 to 5 shift. Okay, what we say 1, 5 NO2 shift takes place. So just listen carefully and look at the structures carefully. Okay, don't get the confusion, and if you get the confusion still now, so please contact me through your personal chat or through the group chat from the mobile app chemmasters. Okay, right. Now in the next step, so the hydrate shift taking place. So I'm going to label 1, 2, 3, 4, 5. I'm going to label the atoms in the way of transferring the electrons. Okay, so that is the important. It is not just like IUPAC priority. It is simply I'm just giving the I'm just labeling the atoms on the way of transferring the electrons. Okay, so that's why here. So the bond breaks here and just moves here. Then this bond moves here and this bond moves onto the nitrogen. Okay, so here after that the new double bond here and new double bond here, and here is a nitrogen, and this electron density of nitrogen abstract this proton. So the proton is here and here is the NO2. So what you observe, the shifting of hydrogen takes place from atom 1 to atom 5. So we can say 1 comma 5 hydrogen shift takes place. So this is the final transformed product is given in the given question. So that's why in the transformation, in the given transformation, we have seen 1 comma 5 NO to 2, 1 comma 5 NO to shifts, and 1 comma 5 hydrogen shift. Okay, so what is the correct answer here? Option 3 is the correct answer. Got it? Okay, right. The next question. Here, so we have designed this question by just taking the concept of violet, that is phosphorus violet. Now try to expand this phosphorus violet here. So PHO, and here PHO, here CH2. Now here we have C double bond O, OET. So this is the structure, and here NaH. We know that which is a strong base and which can abstract acidic protons, and that's why here is a formation of negative charge, and phosphorus with the positive charge. That's why here is a formation of a violet, phosphorus violet. Okay, here the stereochemistry of the product alkene depends on various factors on phosphorus violet. We can come across in our lectures, but here the size of the ester just decides the stereochemistry of the product. Okay, so here, for example, if we take ethyl and isopropyl and tertiary butyl, so by just increasing the size of the groups on the ester, the Z selectivity of the product increases. Just note this important point. Okay, right. And at the same time, just look at the given reagent. We have taken 59%, more than half of it. That means we can say excess reagent is taken. So whenever we have taken excess phosphorus violet, it can react both isolated aldehyde and alpha beta unsaturated aldehyde and converted them into Z alkenes. Okay, so here where you can find Z alkenes in the fourth option, you can see Z alkenes are there. That's why option 4 is the correct answer. Here, so here what is the main factor to design this question? The size of the ester. So here, when you take ethyl, 90% of Z enolate is produced. When you take isopropyl, 95%. When you take tertiary butyl, 99% of Z enolate is the predominant product in the given reaction. Okay, so the size of the ester is the deciding factor, and whenever the size of the ester on the given phosphorus violet increases, then Z selectivity of the alkene in the product is increases. Okay, right. So if you have any doubts, so please contact us through our mobile app. Okay, thank you very much.